Buckle up, buttercups. We're about to shear some pins, fatigue some metals, and maybe even learn something. Mechanical Engineering Made Simple starts now. So this deep dive today is really designed as a foundational lesson.
Yeah, it's entirely for the learner, right? We're addressing the absolute most popular math and foundational questions that, engineers actually struggle with out in the real world.
Exactly. Because we are unpacking the mathematical realities that completely dictate physical design. It's essentially a survival guide for navigating these really common everyday issues.
It really is. And, if you are listening to this, whether you are a seasoned engineer who maybe just needs a quick refresher or just a curious mind trying to understand how physical objects are designed and built.
Yeah, this deep dive is going to give you those critical few mathematical tools, the ones you absolutely need to avoid being mastered by the trivial many.
Right. And to really grasp how we apply this math today, we first have to talk about the evolution of the engineer's workbench.
Oh, absolutely. Because the tools we use, they completely change how we approach the math, don't they?
They do. Let's wind the clock back a bit. Picture an Apollo engineer back in the mid-1960s. They are trying to calculate the structural load on a massive Saturn V rocket.
And they obviously didn't have desktop computers sitting around.
No, not at all. They had the iconic Kiefelin-Esser, the K&E slide rule.
Which is such a magnificent piece of technology for its time.
It really was. Just a straight, sometimes circular or cylindrical piece of wood and celluloid. But here is the critical thing about a slide rule. It doesn't actually do the math for you in the way a modern device does.
Right. You physically slide the components to align these logarithmic scales.
Yeah, exactly. To perform multiplication, division, roots, or trigonometry. It gives you the significant digits, the core sequence of the numbers.
But it doesn't tell you where the decimal point goes.
That's the kicker. The physical artifact gives you, say, the digits 2, 4, and 5. But it is entirely up to the engineer's brain, their own physical intuition, to know if the answer is 2.45 pounds of force.
Or 245,000 pounds of force.
Exactly. The entire burden of magnitude rested completely on the human being.
Man, that requires just an insane level of mental discipline. You had to have an intrinsic gut-level understanding of the physical system you were designing.
Or you would be off by massive orders of magnitude and literally blow up the rocket.
Right. But then, the late 1960s and 70s hit, and the handheld electronic calculator finally arrived on the scene.
And that completely shifted the cognitive load for everyone. We moved right into the era of programmable graphing calculators.
Oh, like the legendary Texas Instruments TI-85.
Yeah, or the Hewlett-Packard 48G. Suddenly you had a device in your hand that could process matrices, graph complex equations on an LCD screen, and crucially,
it tracked the decimal point for you.
It did. It made the job vastly faster.
But I have to imagine it also introduced a whole new kind of danger, right? If the machine is tracking the magnitude, the engineer doesn't have to anymore.
You hit the nail on the head. And that danger multiplied exponentially with the leap to personal computers and WYSIWG software.
Or the WYSIWG. What you see is what you get.
Right. Programs like Mathcad completely changed the game.
Because with those programs, you aren't just punching in raw numbers.
Right.
You are typing the equation onto the screen exactly as you would write it on a piece of paper.
Exactly. The software performs symbolic integration. It handles all the algebraic expansions dynamically. You change one single variable at the very top of the page.
And thousands of calculations update instantly down the entire document.
Yeah. Then you print it out, and it's just this perfect, pristine engineering record.
I look at this reliance on software, and I always compare it to driving a car with GPS.
Oh, that's a great analogy.
It's amazing, right?
Yeah.
It routes you around traffic. It tells you exactly when to turn, optimizes your entire journey perfectly.
It is fantastic right up until the moment you lose signal.
Exactly. Or you drive into an area where the map just hasn't been updated. If you don't know the underlying roads, if you don't know the fundamental math beneath it all, you're going to drive right off a cliff.
Yeah.
So does having incredible tools like Mathcad make modern engineers lazy or just more efficient?
I'd say it makes them profoundly more efficient, but it creates a massive vulnerability, which is the erosion of physical intuition.
Because the software is just a black box.
Right. It blindly follows its algorithms. If you put a flawed assumption into Mathcad, it will give you a highly precise, beautifully formatted, computationally perfect disaster.
Right. It will give you the completely wrong answer to 10 decimal places of accuracy.
Because the computer has no idea if that force calculation is for a tiny latch on a toaster oven 7 or the main support cable of a massive suspension bridge.
It has literally zero physical context.
None. And this is exactly why an engineer must understand why the software outputs a specific number. If your software spits out 4,000 pounds of force, you need the mathematical foundation to look at that and instinctively say, wait a minute.
Like, based on the physical parameters of this specific linkage, it should be closer to 400 pounds.
Exactly. That raw intuition is the only thing standing between a minor typo on a screen and a catastrophic mechanical failure in the real world.
Wow. Okay, so if we want to build that intuition, we can't just trust the black box. We have to understand the physical realities the software is trying to model in the first place.
Right, and to do that, we have to start at the physical level, the shapes that make up the physical world, which brings us to plane geometry.
The physical constraints of reality.
Yes, the study of figures on a two-dimensional flat surface. I mean, geometry isn't just some math class you sleep through in high school. For an engineer, it represents the absolute physical constraints of reality.
I always like to think of the rules of geometry as the gravity of mechanical design,
That's a good way to put it.
because you cannot negotiate with them. If you are designing a mechanical linkage for an aircraft landing gear or a complex gear train for an industrial turbine, those angles and those lengths are absolute ironclad laws.
They are. You can't ask the Ford steel to just bend a little bit differently because your math was slightly optimistic.
You truly cannot. And the absolute heavy lifter, the VIP shape in all of engineering, is obviously the triangle.
Without a doubt.
So let's skip the basic definitions. I think everyone knows that a triangle has 3 sides, and the interior angles always equal exactly 180 degrees.
Right, and you have your isosceles triangles where 2 equal sides mean 2 equal angles, and equilateral triangles where all sides are equal and all angles are exactly 60 degrees.
Yeah, standard stuff. But what I really want to know is how engineers actually use this shape to manipulate physical reality. Let's say I'm designing a massive 500-foot railway truss bridge.
Okay, a huge structural project.
Right. And I need to test how it will handle the weight of a fully loaded freight train. I obviously can't build a full-size prototype just to see if it breaks. That would cost a fortune. I have to build a scale model for the wind tunnel or the stress lab.
Right, you need a manageable model.
So how do I know the desktop model accurately reflects the real thing?
That entire process relies completely on the concept of proportional or similar triangles. This is honestly where geometry becomes a superpower.
How so?
Well, if 3 sides of one triangle are proportional to the corresponding sides of another triangle, say a prime, B prime, and C prime, the triangles are geometrically similar.
Meaning the physical size changes, but the fundamental relationship stays completely locked.
Precisely. If you scale down your 500-foot bridge to a 5-foot desktop model, as long as you maintain the exact ratio of the side lengths, the interior angles of every single truss and support beam remain absolutely identical to the full-size bridge.
Wait, really? The angles are perfectly identical?
Perfectly identical. And why are the angles so important?
I'm guessing because the angles dictate how the actual physical forces are distributed through the structure.
Exactly. A force vector pushing down on a bridge joint splits and travels down the connected beams based strictly on the angles of those beams.
Oh, I see.
Because the angles in your tiny desktop model are identical to the real bridge, the distribution of stress is mathematically identical.
That is wild.
You can apply a known load to your little model, measure the stress, and mathematically scale that force straight up to the real-world massive bridge with total absolute confidence. Because the geometric foundation hasn't changed a fraction of a degree.
That is incredible. The geometry is literally the bridge between the theoretical model and the physical behemoth.
It is.
Now, obviously, we use right triangles heavily, right? The Pythagorean theorem, c squared equals a squared plus b squared. But this geometry applies to circles, too, doesn't it?
Absolutely it does. Think about tangency for a moment.
Okay, tangency.
A line that is tangent to a circle touches its outer edge at exactly 1 microscopic point.
Right.
Geometrically, that tangent line is always exactly 90 degrees, completely normal, to a radial line drawn from the very center of the circle out to that point. Also, all perimeter angles in a circle drawn from the diameter are always exactly 90 degrees.
Okay, but give me a real-world application for that. Why does a mechanical engineer actually care about a 90-degree tangent line on a circle?
Okay, imagine you are designing the camshaft for a high-performance internal combustion engine.
Oh, okay.
The cam lobe is essentially an eccentric circle pushing down on a perfectly flat valve lifter. That lifter represents your tangent line.
Right. They touch at that one point.
Now, if the geometry isn't perfectly calculated so that the downward force is transferred at that exact tangent point, the cam lobe won't just push the valve straight down.
What will it do?
It will push it sideways. It will introduce a lateral shearing force.
Oh, wow.
And in an engine running at 8,000 revolutions per minute, that sideways force will tear the engine block apart in a matter of seconds.
Good grief. So geometry dictates the shape, and the shape dictates survival.
That's a perfect summary.
But physical shapes don't just exist in a vacuum, right? They interact under massive force, which requires us to manipulate complex algebraic equations before we ever plug in a single number.
Right. Moving from geometry to algebra is essentially shifting your focus from just the shape of things to the dynamic relationships between forces, materials, and motion.
And this brings us to the algebra of design.
Exactly. And here is where we really separate the basic button pushers from the real intuitive engineers. The absolute most vital algebraic skill is the ability to transpose and manipulate equations before you ever touch your calculator.
I really want to push back on this a bit because to an outsider, it sounds incredibly tedious.
How so?
Well, let's take a classic heavy-duty mechanical equation. From our source material, let's look at this one. R equals the quantity g multiplied by d to the fourth, divided by the quantity 8 multiplied by n multiplied by d cubed.
Ah, yes, a classic.
You are calculating variables for torque, diameter, all of it. Why on earth wouldn't an engineer just immediately plug the known numbers directly into that raw equation, hit enter on their software, and just get the answer?
People ask that all the time.
Like, why painstakingly rearrange a bunch of letters on a whiteboard first to solve for little d? I mean, solving for d means taking the fourth root of the quantity r multiplied by 8 multiplied by n multiplied by d cubed, all divided by g. It feels like academic snobbery to do that by hand first.
I hear that complaint often, especially from junior engineers, but I assure you it is the exact opposite of snobbery. It is about revealing the physical truth of the system.
The physical truth.
Yes. When you just look at an equation filled with raw numbers, it is just a chaotic jumble of data. Your brain can't parse the relationships.
Okay, I follow you.
But when you isolate the variables and transpose the formula using just the letters, you expose the raw levers of the physical world. You see algebraic expansions, like the binomial formula, or how factoring simplifies a complex interaction.
Walk me through what you mean by exposing the levers in that specific equation.
Okay, let's look at your transposed equation where we solved for little d. Or even better, let's look back at the original, where we solved for r. Notice where the big D is.
The big D is in the denominator, and it's cubed.
Exactly. Big D is sitting in the basement of the fraction, and it is cubed. Because you are looking at the pure algebra, you can instantly see that big D has a terrifyingly outsized impact on your final result for R.
Because it's a cube in the denominator.
Right. If you slightly increase that D variable, you are instantly going to massively decrease R. You just know that intuitively because of how the letters are arranged.
Oh, wow. Because cubing even a tiny increase makes the bottom of the fraction huge.
Exactly. You realize, hey, I don't need to completely redesign this entire system. I just need to tweak this one dimension, and the stress drops off a cliff. You completely lose that intuitive understanding if you just smash numbers into a calculator right away. The algebra tells you what physical property actually matters most.
It is quite literally the blueprint of the physics.
Mm-hmm.
That makes total sense. But algebra also throws some curveballs that seem to defy physical reality, doesn't it?
It does.
Let's talk about quadratics and cubics. We all know how to solve quadratics using the quadratic formula. But specifically, I want to ask about the determinant.
Ah, yes. The classic b squared minus 4ac, the part of the equation sitting under the square root.
Right. We know that if that determinant, b squared minus 4ac, is negative, we end up trying to take the square root of a negative number.
Which results in an imaginary root, using I, right? Which is defined as the square root of -1.
Exactly. In pure math, that's just another Tuesday. But in the physical world of mechanical engineering, what does an imaginary number actually mean? Does the machine teleport to another dimension?
No teleporting, sadly. In a physical design problem, an imaginary root is essentially a mathematical stop sign. It very often represents a physical impossibility.
Wait, an impossibility? How so?
Okay, let's say you are programming the kinematics for an industrial robotic arm on a fast-paced manufacturing line. You set up a quadratic equation to calculate the exact time it will take for the robotic gripper to intercept a moving part on a conveyor belt.
Okay, pretty standard problem.
You run the algebra, and your time variable results in an imaginary number.
So what is the math actually telling you there?
It is telling you that under your current physical constraints, the speed of the belt, the maximum acceleration of the arm's motors, the distance the arm will absolutely never intercept the part.
It's just physically impossible.
Right. The mathematical curve of the arm's reach and the path of the part simply do not intersect in real physical space. If you ignore that imaginary number and try to force the system to operate anyway, the robot will literally rip itself off its mounting bolts trying to achieve infinite acceleration to reach a point that doesn't exist in its timeline.
Wow. The math is literally screaming at you that you have designed a failure.
It is. Now, to be fair, complex numbers, where you combine a real number and an imaginary number, explaining its polar form using modulus and amplitude, or zeta, those do have profound uses in engineering.
Like where?
Particularly for mapping rotational dynamics, fluid flows, and oscillating systems. But when you are solving for a linear physical state like the robot arm, and you hit an imaginary root, you have to completely rethink your physical parameter.
Okay, so we use algebra to understand the relationships and spot possibilities.
Right.
But sometimes the numbers we derive are so massively large or so infinitesimally small that standard algebra just completely breaks down without specialized notation.
Oh, absolutely. That is when we cross the threshold into managing extremes, and that requires a totally different set of mathematical tools.
Which brings us to powers of 10 and logarithms.
Yes.
Now, scientific notation, powers of 10, I can wrap my head around that. We use it to compress absurdly large or microscopic numbers to make them legible.
Exactly. You just move the decimal point and count the jumps.
Yeah. Right, so if I have an engine clearance of 0.0001759 inches, I just write that as 1.759 times 10 to the negative fourth power.
Spot on. And in engineering calculations, we almost exclusively group these powers in multiples of 3.
Multiples of 3, why?
Because it maps to our standard prefixes. 10 to the third is kilo, 10 to the sixth is mega, 10 to the ninth is giga. It just completely standardizes the language. When you say a material has a tensile strength of 400 megapascals, every single engineer instantly knows the magnitude without having to stop and count zeros.
Oh, that makes a lot of sense. But writing the numbers is one thing. Calculating forces that grow exponentially over time is another beast entirely.
It is. And this brings us to logarithms, which are the ultimate tool for dealing with exponent power.
I have always thought of logarithms as a way to fold a massive sheet of paper.
I love that analogy.
Yeah, you start with this sprawling, totally unmanageable sheet that represents massive exponentiation, and the logarithm just folds it down, compressing it into a manageable linear space. It turns exponentiation into simple multiplication, and multiplication into simple addition.
That is a phenomenal way to visualize it. Logarithms compress the scale of reality so our brains can actually work with the math. A logarithm is just the exponent to which a base must be raised to produce a given number.
And we distinguish between common logarithms, which use base 10, and natural logarithms, which use base e, right?
Yes, base e, which is roughly 2.71828, and you can use the modulus to convert between them. When you are dealing with explosive compound growth, those logs are the only mathematical levers you really need.
Let's walk through a specific compound rate example. Let's say you have a company of 250 people, and it is growing at a rate of 15% per year.
Okay, a classic growth problem.
Right. And you want to know exactly how long it will take to triple in size to 750 people. If you set that up, it looks like 3 equals 1.15 to the power of n.
Right, where n is the number of years.
Now, without logarithms, how do you even solve for an exponent like n? You'd just be guessing and checking forever.
Exactly. But with logarithms, you just bring the exponent down.
So it becomes n equals log 3 divided by log 1.15.
Which solves to roughly 7.86 years. The log just snaps that exponential problem into a simple division problem.
It's brilliant. Now, how does that actually connect back to engineering?
Oh, logs are essential for calculating anything that degrades or grows at a compound rate over time. Heat dissipation through an engine block, thermodynamic decay, or let's talk about a life or death scenario, material fatigue.
Oh, like metal fatiguing over time.
Exactly. Have you ever heard of the de Havilland Comet? It was the world's first commercial jet airliner in the 1950s.
I have, yeah. It was a marvel of engineering, but didn't several of them tragically disintegrate mid-flight?
They did, and the cause was metal fatigue. Every single time the aircraft climbed to altitude, the cabin was pressurized, acting kind of like a balloon expanding, and when it landed, it depressurized.
So it's just expanding and contracting over and over?
Right. These cyclic loads created microscopic cracks at the corners of the windows. But the crucial part is how those cracks grew. Crack propagation in a stressed material does not happen linearly.
It doesn't just grow 1 millimeter every flight.
No, it grows at a compound exponential rate. A microscopic flaw becomes a hairline fracture, which compounds into a visible crack, which then catastrophically tears across the entire fuselage in a fraction of a second.
It accelerates.
Exactly. If you want to predict when that metal will fail, you cannot use standard algebra. The equation for fatigue life involves taking the number of cycles to failure, which is an exponent.
Ah, so you have to use a logarithm.
You have to take the logarithm of both sides of the fatigue equation to bring that exponent down to the baseline, allowing you to actually solve for the number of flights a plane can safely make before it must be retired.
Wow. So without logs, you cannot predict the failure point? You are quite literally just guessing when the plane will break.
Exactly. Any natural phenomenon that degrades or grows exponentially is modeled using logarithmic curves.
It takes the terror of exponential growth and turns it into a predictable line.
Exactly.
Okay, so having tackled the magnitude of these numbers, we must return to how these massive forces actually apply to physical angles.
Which brings us to the engineer's secret weapon, and honestly, occasionally their worst nightmare.
Trigonometry.
Trigonometry.
Now, we all know the fundamental functions of a right triangle: sine, cosine, tangent, opposite over hypotenuse and all that. And their reciprocals: cosecant, secant, cotangent.
Right. And historically, there were actually some lesser-known functions, too, like the versine, the coversine, and the haversine.
Which sound a bit archaic now, but they were crucial before calculators.
Yeah.
But the real world is almost never built out of perfect 90-degree angles, is it?
No, it is not. If you are designing the tubular space frame of a race car or the boom of a massive construction crane, you are dealing with oblique triangles, triangles with no right angle at all.
And to solve those, to figure out the forces acting on those weird angles, we use the law of sines and the law of cosines.
Correct. The law of sines is very elegant. The ratio of a side length to the sine of its opposite angle is constant for all three sides. And the law of cosines allows you to find a missing side if you know the other two sides and the angle clamped between them.
But this is where the math can actually lay a massive trap for you, right? Let's explicitly walk the listener through the ambiguous case, because just the name sounds like something you want to avoid when building a bridge.
Oh, you absolutely want to avoid it. Case 2, the ambiguous case. This occurs when you are given two side lengths of a triangle and an angle that is not clamped between them. It is opposite one of the sides.
Why is that a trap?
Because when you run that data through the law of sines, it doesn't just give you one guaranteed answer. The math might tell you that there is one perfectly valid physical solution.
Okay, that's fine.
Or it might tell you there is absolutely no physically possible solution.
Okay.
Or, and this is where engineers lose their jobs, it might tell you there are two completely different mathematically valid triangles that satisfy those exact same inputs.
That is insane. Give me a physical example. How can a physical object exist in two ways?
Okay. Imagine you are programming the hydraulic cylinders on a heavy excavator. You know, the kind used in massive mining operations.
Right.
You know the length of the boom, you know the length of the stick, and you know the angle of the hydraulic ram pushing on it. You punch those numbers into the law of sines to find the exact position of the bucket.
Sounds standard.
But if it falls into the ambiguous case, the trigonometric math says the bucket could be fully extended out in front of the machine scooping dirt, or it could be swung violently back, completely trashed through the operator's cab. Both physical positions completely satisfy the exact same trigonometric inputs.
Oh my God. So if the software doesn't know which physical reality you actually intend, the machine will act unpredictably.
Exactly. If you don't recognize the ambiguous case, you might command a mechanism to move, and it violently snaps into the alternate geometric reality, completely destroying itself and anyone around it.
That is utterly terrifying. But let's say you avoid the ambiguous case.
Okay.
Let's walk through the source example. Say you are solving an oblique triangle with known angles of 40 degrees and 98 degrees.
Well, calculating the final angle is easy because they have to add up to 180, so the final angle is 42 degrees.
Right. And then you can use the law of sines to find the missing sides, which in this specific example come out to 9.608 and 14.801. But here's my pushback. Doing all this math by hand, juggling all these sines and cosines across multiple linkage points, It leaves a massive amount of room for a simple arithmetic error.
Yeah.
One dropped decimal point, one rounded number early in the process, and your multi-million part jams and breaks. How do you actually verify your work? How do you trust your result?
You absolutely need a safety net, and the ultimate safety net is called the Moll-White equation.
The Moll-White equation, how does that work?
Well, when you use the law of sines or cosines, you are usually only working with 3 parts of a triangle to find a 4th part.
Right.
The Moll-White equation is brilliant because it involves all parts of the triangle. It incorporates all 3 side lengths and all 3 interior angles simultaneously, making it the perfect self-check mechanism.
Oh, it forces the whole system to account for itself.
Exactly. It sets up a ratio of the side lengths on the left side of the equal sign and a complex ratio of trigonometric functions of the angles on the right side. Once you have solved your entire triangle, you plug every single number into the Moll-White equation.
And if you made even a microscopic error?
The equation will categorically refuse to balance. But if both sides of the Moll-White equation balance, like the example in our text where the left side calculates to negative 0.257.
And the right side calculates to negative 0.258.
Right, allowing for that tiny fraction of rounding difference. If they equal out, the engineer knows for a fact that the geometry is completely sound. It is the ultimate mathematical proof of reality.
Okay, so trigonometry locks down static shapes, and the Moll-White equation double checks it.
Yes.
But mechanical engineering is rarely just static shapes. It is fundamentally about continuous motion, dynamic forces, fluid flow over a wing, the dynamic rotation of gears. For that, static triangles just aren't enough.
No, they aren't. To capture motion, we turn to curves and calculus. This is where we introduce analytical geometry, which marries the equations of algebra with the physical space of geometry to map complex curves.
Now, we all grew up with standard rectangular coordinates, the standard X and Y grid. But when dealing with rotating machinery, that grid is incredibly clunky.
Extremely clunky. Contrast that standard rectangular grid with polar coordinates. If you are analyzing a spinning flywheel or a turbine blade, you don't care about X and Y. You care about distance from the center and the angle of rotation.
And polar coordinates map a point using only the radius and the angle.
Exactly. It allows you to mathematically model rotational dynamics seamlessly.
And using these coordinates, engineers map some crucial curves. We have the parabola, the catenary.
Which is the hyperbolic cosine dictating the shape of a hanging cable.
Right, and the spiral of Archimedes. But the one that absolutely blew my mind was the involute of a circle.
Ah, yes. The involute of a circle.
To me, that just sounds like an obscure magic spell. I cast involute of a circle.
It does sound a bit arcane.
But there's a great analogy to visualize it. Imagine a solid metal cylinder sitting on a table. Now imagine you have a piece of string tightly wrapped around that cylinder.
Okay, a taut string.
You tie a pen to the loose end of the string. Keeping the string pulled absolutely taut, you slowly unwind it from the cylinder, drawing on the table as you go. That expanding, spiraling curve that the pen draws is the involute curve.
That is a perfect visualization, the string unwinding from the cylinder. Now, why does a mechanical engineer actually care about that specific shape?
Right. What is the application?
Because that specific mathematical involute curve is exactly how modern gear teeth are shaped.
Wait, really? The gears in my car's transmission?
Almost all of them. Here's why. If you just cut gear teeth as simple triangles or square blocks, as the gears rotate and the teeth mesh, the exact point where the teeth touch would slide back and forth.
Which means sliding friction.
Massive friction, heat, and vibration. The speed ratio between the two gears would constantly fluctuate microseconds at a time. The gears would chatter. At thousands of RPM, non-involute gears will grind and explosively shatter in seconds.
But because of the involute curve.
Because of the unique mathematics of that unwinding string, when two involute gear teeth mesh and roll against each other, they ensure smooth, continuous power transmission without grinding. The point of contact moves along a perfectly straight line, and they literally roll perfectly against each other.
That is an incredible realization. The abstract math of a curve directly translates to the survival of a machine.
It does.
But identifying the curve is one thing. To truly manipulate it, to find its dynamic limits, we need calculus in action.
Yes. Calculus is the mathematics of change, and the foundational tool here is the derivative.
Now let's define the derivative without the scary math symbols. We always see dy over dx. What does it actually mean?
Stripped of the notation, the derivative simply calculates the instant rate of change of a function. It is the limit approached by the increment of y over the increment of x as x approaches 0.
So in the real world, what does that represent?
It represents the physical slope of a curve or the instant velocity of a moving particle. If you were driving a car, algebra tells you your average speed over the whole trip. The derivative tells you exactly what the speedometer reads at the precise millisecond you pass mile marker 50.
But the place where the derivative truly pays the bills for engineering firms is in optimization problems, right? Finding the absolute maximum or minimum limits.
Optimization is the holy grail. How do we make the strongest possible beam using the least amount of titanium? Calculus answers that. Let's walk through a maximum-minimum optimization problem.
Okay, let's hear it.
Imagine you are an engineer, and you have exactly 50 square feet of material to build a container.
Okay.
And this container has square ends. Your boss tells you, maximize the internal volume of this container. How do you find the exact dimensions for maximum capacity?
Well, you start by defining your constraint, right? The 50 square feet. So you set up a surface area equation. Since the ends are square, if the height and width are x, the area of the two ends is 2 times x squared.
Right. And the four sides have a length we will call y. So their total area is 4 times x times y.
Meaning the total surface area constraint equation is 2 times x squared plus 4 times x times y equals 50.
Exactly. Now you use algebra to isolate the variable y. When you do that, you get y equals the quantity of 50 minus 2 times x squared, all divided by 4 times x.
Okay, so we've isolated the length, y. Now we look at our goal, which is maximizing volume.
Right. The volume equation is x squared times y.
So we take that algebraic expression for y that we just found and substitute it directly into the volume equation.
Precisely. And now you have a single equation for volume that only contains the variable x. And this is where the derivative works its magic. If you graph that volume equation, it would look like a giant arch. The absolute highest peak of that arch is your maximum possible volume.
And at the exact peak of an arch, the curve stops going up but hasn't started coming down. The slope is perfectly flat.
The slope is 0. And because the derivative is the slope, taking the derivative of that volume equation and setting it to 0 is exactly how you find the exact dimensions for maximum capacity.
You literally set the derivative to 0, solve for x, and the math hands you the perfect dimension. It's a mathematical certainty.
It is absolutely brilliant.
Which brings us full circle, really. We started this deep dive talking about the incredible power of modern software Mathcad, TI calculators, 3D modeling suites.
And it is true, those tools can instantly optimize that volume or map an involute curve in a microsecond. But here is my final thought on modern engineering. While those tools are incredibly powerful, they lack physical intuition.
They really do.
If an engineer inputs a flawed assumption into that software, the software will confidently output a perfectly calculated disaster. It won't warn you that your container is structurally impossible in the real world.
So the true skill of an engineer isn't doing the math.
No. The processor in your laptop does the math. The true skill of an engineer is knowing which math applies to the reality of the physical problem in front of them. It's having the intuition to know when the computer is right and when the computer is about to build a bridge out of paper.
Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.